All right, folks, welcome back. CE 529. We are talking about sort of a discussion on dynamic traffic assignment. But before I do that, just to clarify a few things, housekeeping type items. I will assign a new homework that will be due Tuesday. So look for that later before the lab today. So that will be sort of another opportunity to maybe, if you get done with the lab today, which is sort of you just have to show me your network that's working. And then we're going to extend that network that you built in the last session to include now, not just the two two-way stop control intersections, but to now add some pre-time signals. I used to be able to do the actuated signals in this class, but vSim just sort of messed up their license thing. And now the student version only allows you to do pre-time signals and doesn't allow the RBC signals. But that's still okay, because I think that can still give you some practice on how to model coordinated signals. Usually none of the isolated sort of traffic signals are pre-timed anymore. You know, if you have an isolated signal, you always have detectors and they actuate the signal. So I would have really loved for you to have the ability to be able to model actuated signals in the class. But it looks like vSim student version doesn't really allow that anymore, which is fine. I'll still give you the sort of the instructions on how to do that. So if you ever, I would have to actually model those types of signals, you can, and you'll have some sort of resources to be able to do that. But so what we're going to do is try to wrap up the lab today by adding a couple of traffic signals on the network. And then I'll go over some of the concerns that I noticed as we were walking around the other day. So I think there were some concerns related to sort of where to put the stop sign. And there were some students were having some issues with routing. So I'll make sure that, all of us are on the same page with those things. And then obviously, there was some issue with how I had described to get the output, and that didn't quite exactly work. And I think this is probably has to do with the sort of the different versions. So we'll take care of those issues today. My goal will be to sort of wrap up the vSim tutorial, assign the homework, and then, go from there. Okay, any questions about this? Questions? So what I'll do is I'll go ahead and start sharing my screen. We were talking about sort of this idea of what happens when your demand just exceeds the capacity of your network. You have 4,000 vehicles per hour demand, and what does that mean for the equilibrium that might happen, right? So under the equilibrium scenario, you'll come up with these volumes, 1,500 and 2,500 for both of these links. So the green link will have demand exceeding capacity, and then in this scenario, just the solution, what would solution look like? If these were your curves, what would the equilibrium solutions might look like, right? So this is just a graphical way of representing solution. And how did I find the solution? I found the solution by just thinking about the travel time has to be equal. So I can just put a horizontal line through this chart, right? Because the travel time on both routes have to be equal. So I pick up any travel time or the travel time and pull this line out. And then where does that intersect for, where does that, like the total becomes 4,000 at those demand levels. So obviously I could have drawn a line here, right? There could have been a line drawn. So let me annotate that a little bit. See if we can. You could think about drawing lines here as well, right? You could have drawn a line here, right? But then you'll have to draw some lines here as well to think about what's the total demand that you're able to serve. So you could have drawn a straight line at any given travel time. Look at what is the total demand that you're able to serve at those demand levels. And then when I do this by randomly picking a spot where I'm just calling it 75 minutes, and then drawing the demand back down level, that I'm just showing that this would be sort of one way of sort of graphically finding the solution. I'm not going to ever ask you to find the solution graphically, because that involves a lot of trial and error. But there is a problem with the solution, by the way. So what's the problem here? The problem with the solution is that once the link demand exceeds capacity, so in the green link, the demand is now 1500 as opposed to 1200. That is the capacity of the link. And then demand here is 2500 as opposed to the capacity of only 1800. Now, these volume delay functions are not very well defined once you exceed the capacity. So your equilibrium solutions are going to be unreliable, because if you remember, I showed you this chart, right? This is the real world data that I showed you. You can pretty much do a good job of sort of maybe coming up with a demand until in this unsaturated flow conditions. But once you hit that, this model is sort of not very well defined. How the link travel time behaves, once you exceed the capacity. So your static equilibrium issues will always have some issues related to this, because your volume delay functions are not very well defined for any link that once that exceeds capacity. So once V by C ratio, the volume to capacity ratio goes above 1, you are sort of in trouble. Right? So that's the big problem here. Yes. So how does it matter? Like if they're not defined, they're not well defined. But the problem is, once V by C exceeds 1, demand exceeds capacity, you know that congestion will happen. But you have no idea how. So at V by C, let's say 1.1, two very similar links, or the same link on the same day when the demand is 110% of the capacity, the queue lengths could be wildly different. The delay, the travel time could be wildly different. You just don't know. Because as I showed you that real data link, right? The dots were all over the place. You could see it in this chart here. That let's say your demand exceeded, so let's say the capacity is 2000. You can find at 2000, any flow exceeding 2000, you could be this point, this point, this point, this point, this point. You just don't know which point are you going to be at once the demand exceeds capacity. So once you go above, let's say, if the capacity is 1800 or 2000, once you exceed that level, all these data points could line up wherever. You just don't know. From day to day, the things are just, the curve could be very well defined over here. You could see that, most of these points fall into that. But once you in that saturated flow category, all bets are off. So that's the problem, is why when V by C exceeds 1, you really don't have good relationships between travel time and queue length and all these measurable things that you can actually measure. They could be all over the place. Okay. And that's why static assignment works well when you have sort of moderate to sort of under the capacity condition. But once you exceed those, all bets are sort of off. You don't know how the queue lengths are going to be, how the speeds are going to be. So your real bet is just to kind of go out and observe and figure that out. So that's why you need something that sort of works in the, so dynamic traffic assignment can help address that problem. So dynamic traffic assignment is a route modeling approach that captures the relationship between dynamic route choice behavior, path, and starting time. So you can, so now you're thinking about, okay, now I'm not just choosing paths. This is the most important thing about DTA, right? That in static assignment, always we describe the problem as, you choose your route. What route would you choose? We never really worried about what time would you start. Now you can think about, okay, in the real world, your start time also has pretty good implications, pretty significant implications for how much travel time you end up with. So your dynamic route choice behavior should include path, but also the start time. Okay, and then the transportation network characteristics as well. So and it assumes that travelers know future travel time along the journey. You're able to capture the traffic flow variations, and then signal and intersection design matter in congestion management. Okay, so if you're trying to manage congestion or flow through congested street, then you can, you have to kind of account for all these signals and intersection design, traffic flow variation, and then the travel time. So DTA and simulation. So where does DTA fit into simulation approaches, right? So newer route microscopic models like vSim, for example, they're route based. I think you're learning that in your lab. Maybe you don't like it that much, but they are route based, right? They have to be route based, meaning we can select a route at departure and follow that route either with update or without update. So even when you're doing static assignment, you're defining those static route choices. One shot sort of non-iterative assignment simulation approach is that vehicle departing at different times, they're given a route that might be periodically updated in simulation based on what we call the instantaneous travel time. And we'll talk a little bit more in depth about this. We're even going to solve some problems on this instantaneous travel times. And then some models allow the en route vehicles to update their routes based on, even after they depart, there might be nodes in the network where they can update their paths. While this is all sort of good, most travelers, they might not be choosing their routes based on sort of, that instantaneous experience. They might be looking at experience travel time. So it might be, some of their past experience in real world, like thinking about how people choose route. That's just based on their sort of historical experiences and so on. If that is the case, now you have to somehow anticipate the future. So what happens is in dynamic traffic assignment, it's not just, you assign the traffic flow, you assign the proportions like you've been doing and like you would be doing in this class. Instead, you let it happen. You let the travelers experience some travel time. And then you let the algorithm converge. So basically what would happen in a dynamic traffic assignment scenario, I don't think the student version can do that. But there are ways of doing that. It's that you define your zones, origins and destinations and all that. And you assign certain routes to traffic, like, okay, these are sort of my primary routes. You don't assign the exact flow that goes into each of those routes. You just give them like, okay, from this OD pair, this is the demand, and you route it for them, okay, in simulation. So vSim would run sort of one iteration of the network, and then it will say, okay, I'm going to do one more iteration of the network and see if, based on what I learned from the previous run, can I adjust my route and save on travel time? Okay? And then it'll keep doing until adjusting either the path or the start time. Right? So basically you assign a window of, okay, you want to update travel times every 1 minute, every 5 minutes, every 15 minutes, whatever it is. And then the model will check, is that, is it worth sort of doing another iteration? From previous iteration to the next iteration, is my travel time savings are significant? So, and you specify what your threshold for that, what's at what point you stop iterating anymore. Okay, so this is sort of an iterative approach that vSim takes. And again, I'm explaining to you the big picture of how it works. You don't really, I don't think if you got the traffic assignments, you could do it right now. If you just gave me one problem on like vSim, I could probably simulate it. I don't know. So this is another problem. Like when your network is larger, you have a very big network in your thing, in your vSim model, the dynamic traffic assignment can be almost impossible to converge also. So you only are able to do dynamic traffic assignment because such a detailed model, when your network is a little in a microsecond, of course, in macro level, we can do it. when you're not concerned about individual vehicle movement. But if you're microscopic modeling a very big network, DTA, the dynamic traffic assignment equilibrium, would be hard to achieve. The convergence just won't be easy to get, okay? Because there would be like too many signals, and every iteration, there might be things that change, and you might not be able to get consistent results. And we did face that in a project. We were trying to model the evacuation of the downtown San Jose area, and this was like maybe 8-9 years ago, something like that. So we modeled the network in vSim. We tried to get the dynamic traffic assignment going. We made it work. I mean, I didn't make it work. My student made it work. And when they made it work, they just never could get the convergence. So they figured out how to model it. They had a very big network. They tried to get the convergence. That didn't work. So then we said, okay, let's try to shorten the network. And we kept shortening it until we were left with like maybe about 4 square miles of network. Then we could get the convergence going with the dynamic traffic assignment. Okay. And if the network is any bigger than that, your only hope is that you can. And it's not that I'm saying that you could do it today. It was not the computational capabilities, even though these iterative processes take a lot of time and computing power. But it wasn't the issue with the computing power necessarily. It's just that the network is too complicated. There are too many signals that you can encounter that might be read. There is just no sort of consistency between iteration to iteration, and you are not able to get that convergence that you're looking for. If your network is large enough. If the network is small enough, you could do that. So for example, the Cal Poly network that I showed you, we could potentially get that to work with dynamic traffic assignment. That's reasonable to do because there are not as many traffic signals that might work. Yes.
So for a larger network, you're saying like the best we can do is like somebody will choose a route and like basically has to stick with that no matter
what.
what.
And then not even that, like so they'll have to stick with that, but plus also you're just going to define the traffic flow, and then it's just going to try to route that traffic through there. And that might be okay for most situations. I'm not saying that that's a bad approach, but the trade-off is if you're doing detailed modeling, so there are sort of 3 things, right? How big your network you're modeling, how detailed you're modeling, and then are you doing, and between the details, are you modeling like vehicle to vehicle interaction, or are you just looking at macro level models? And then the third thing is like, could you be happy with the static side? So you almost have to pick, maybe 2 things, right? So it won't be, so you have to pick either, if you're doing dynamic traffic assignment, then maybe your network can't be too large. Or dynamic microscopic simulation, your network can't be too large. And I don't know, there's no hard and fast answer as to, so if you have not as many signals, maybe you can get away with that. Maybe you can get away with modeling a large network. But so that sort of is the idea. That sort of makes sense. So that's why DTA and simulation have, let's say, like complicated relationships. So if you need it sometimes in certain situations, but if you're trying to do it, don't make your network too large where you are dealing with like too many signals and too many sort of variables that can cause differences in travel time from iteration to iteration. So the DTA equilibrium characteristics, a vehicle departing at different times are assigned different routes. So when I say the travel time has to be equal in the static assignment, now we'll still say that the travel time still has to be equal, but only for the vehicles that depart at the same time. If you depart at the same time, your travel time must be equal. That's what you're going to. Vehicle departing at the same departure time between the same OD pair but taking different routes should have the same experience travel time. Right? So you want to be able to experience that same travel time. Obviously, you can see the problem here because the experience travel time cannot be realized until the trip is over. How would you know what the experience travel time is until the trip is over? And that's the same thing, right? When you're choosing the route, it's based on your past experience. That means that you've taken some past trips in there. So basically what you need to do is you need to make some guesses around experience travel time. So that's where iterations come in. So you experience travel time from the previous iteration, you use it, and then you see if they were able to further minimize their travel time within that sort of convergence threshold that you might specify. Okay, so here is sort of the big picture. The two key ideas here are, how does the DTA extends? How does the DTA extends the static equilibrium idea? It does it in two ways. First extension is it generalizes the static model's perfect information assumption. Right? We always assumed that the drivers knew what was going on in each route, how much travel time would they take. Now we are generalizing it that they're actually gaining that experience via experience. They're learning that via experience. Okay? So they're experiencing a travel time in the previous iteration, and they're using that knowledge to then get around. So we are generalizing that perfect information assumption that we had, that we always assumed, but now we are sort of relying on their actual experience from the previous iteration. So we are able to generalize that assumption. And then the second extension is equal travel time on all used routes still applies, but now it only applies to vehicles or the users that depart at the same time. Okay? And that's again, a level of detail that you can sort of control. Like, are you going to model this every minute, every 5 minutes? What does same time mean, basically? I'm saying here, equal travel time on all used routes only apply to travelers departing at the same time and between the same OD pair. Obviously, that is a given, right? Same OD pair is a given even for static routes. So equal travel time on all routes only apply to travelers departing at the same time. Now that same time could be a 1 minute window, could be a 5 minute window, could be a 15-minute window, depending upon how detailed you want to get. And obviously, the work will be more computationally extensive when? Which one would be more computationally expensive to do if you chose like a 1 minute window or a 5 minute window to define same total? Yeah. The 1 minute window, obviously, right? Because now you have to establish those equilibrium every 1 minute. So anybody who lives between 7 to 7.1 from same OD pair has to have the same time. But now because you can see, right, if you keep sort of increasing that time window, looking at the second extension, let's say you increase that time window to the whole time of simulation. What have you done? If you extend, yeah, you get the static equilibrium, right? Does that make sense? So when I say equal travel time on all used routes only apply to travelers departing at the same time, and now I'm saying same time means basically my whole window of simulation. That's basically what you're doing right now when you're doing static assignment, right? So I'm not generalizing that at all. And obviously you're not doing iteration, so you're not doing the first extension, but in terms of the second extension, when you do the dynamic assignment, okay, and then what I'm saying is that vSim can implement this for you. If you assign all these parameters and all these networks and everything like that, vSim can do that for you. And in vSim, you assign those zones, like, they're defined, like they're called parking lots. So basically that's where they become sort of the source and the sink of the traffic. So that it's doable. It's not like you cannot learn it, but it's just that this is sort of beyond the scope of what we can do in like 6 weeks left. Yeah.
Does our simulation start with no? Or is that?
So yeah, we have to have some warm-up period. So it starts with no. So it starts with like, and this is again something that I want to talk about when you do build the real net, start building the real networks, is that our simulation model will always start with no vehicles on the road, right? So when you are doing, let's say you're collecting the data on travel times and stuff like that, and this applies to regardless of whether you're doing dynamic traffic simulation or static or whatever you're doing. This is very important that when you are averaging travel time, you don't start measuring right away. You give it some what we call the warm-up period. So you basically let the network warm up, get it to your analysis period between 4 to 5 p.m. or whatever it is, and then use that information then to make decisions, but only the information that comes out of after the warm-up period has been exhausted. And then obviously that warm-up period depends on, if you have a very small network, it will get clogged up with vehicles, or it will get vehicles wherever they need to go. So for example, the network that you're modeling right now in the class, in the lab, that network is it's fairly small network. So even like maybe 3-minute warm-up period would be enough. Basically, how do you think about warm-up periods is that how much time would it take for your vehicle starting at one location to reach the end point of the network on average, especially at least in the free flow travel time at the beginning. So give it that at least that much time of warm-up period. So bigger network might need as much as 15 minutes of warm-up travel time, but a small network like yours, maybe 2-3 minutes of warm-up travel time. Warm-up time would be sufficient. Okay? So yeah, so we always start with an empty network and we start feeding traffic. Okay. So now let me sort of define instantaneous travel time and experience travel time. Okay, so a more advanced approach which updates the shortest routes regularly based on prevailing traffic conditions. Okay, so you want to figure out the instantaneous travel time, and then we have to look at sort of the experience travel time. In addition to the above assignment approach, each vehicle reevaluates the current route at each decision node. Okay, based on the current travel time. So experience travel time requires more updating, and you update your travel times at every node. Okay, and then so let's kind of do one example of this in a very, very simple network. Okay, so we are doing sort of instantaneous travel time calculation and experience travel time calculations. And with me. So these boxes, so first of all, these are your nodes. These are your nodes. Like this is this node, the first one. This is your origin node. And then I have another one here. That is my destination. And then you have two sort of intermediate nodes. So you have two more, and think of those as sort of decision points. Think of those as a decision point. These boxes represent the travel time on each of these links. So I'm not giving you, so because I'm trying to simplify the problem, I'm not giving you equations of the link performance functions anymore. I'm giving you these sort of easy to interpret link performance function. All I'm telling you is if you depart the time, if your departure time from the origin, if your departure time for this origin is t equal to 1 minute, at minute t1, if travel time for departing at minute 1, it will take you 1 minute to get through this link. Okay, so that's this one. It'll take you 1 minute to get through this link. That's another one. And 1 minute to get to this link. That's another. That's the 1 minute. So these bottom of these boxes represent if your travel time for departing at minute 1. Okay, and these are sort of what we call the instantaneous travel time at t equal to 1. Now, if you leave your network, if you leave this point at t equal to 2, what this box is telling you is that this link will take 1 minute. This box is telling you this link will take 2 minutes. This box is telling you this link at that time will take 3 minutes. Now, when your modeling is based on instantaneous travel time, you make your decisions for routing and stuff like that. And then this is the origin, this is the destination. You just say, okay, I'm going to start routing my vehicles at leaving at t equal to 1 here to here. They're going from at t equal to 1, they're leaving here and they're trying to go here. How much would there be travel? Would their travel time be? I'm just going to add up 1 plus 1 plus 1. I'm just going to look at what's happening at t equal to 1 at all of these routes. I'm just going to add up the travel time. And I'm going to make my routing decisions based on that 3 minutes of travel. Now, if they all leave at t equal to 2, whatever vehicles now leave the origin at t equal to 2, they'll take 1 minute on this link, 2 minutes on this link, and 3 minutes on this link. And their travel time from origin to destination will be 1 plus 2 plus 3, 6 minutes. Okay. So I make my decision at the time of departure based on at that departure time, what's going on. So one thing is that I'm not updating the travel time at these intermediate nodes at all. I'm just kind of going by whatever is the instantaneous travel time was when I left the origin. Based on that, I'm making the travel time decision. Now let's say, so this box obviously represents what happens if you leave at t equal to 3, right? These boxes represent what happens at t equal to 3. Okay, these boxes represent the travel time on individual links, what happens at t equal to 4. Okay? And then so on and so forth. So you can keep going up and up. If you have t equal to 4, 5, 6, and 1. Now tell me, what would be your instantaneous travel time calculations for this network if you left the network at t equal to 3? At t equal to 3. If you left the location at t equal to 3, what would happen? Yes. 10 minutes. So let's see how you got the 10 minutes. You took 2 minutes on this link, right? If you left at t equal to 3, you would anticipate using 2 minutes on this link. You'd anticipate 3 minutes on this link, and you'd anticipate 5 minutes on this last link. So 2 plus 3 plus 5 will get you 10 minutes. Okay. Now let's make sure that we understand this. At t equal to 4, everybody, can you get the time? If you can't get the time, so t equal to 4, how much time would it take? If you are deciding the travel time, what's that? 11 minutes is exactly right, because you are going to add up 2 minutes on this link, 3 minutes on this link, and 6 minutes on this link. So that's your instantaneous travel time calculation. Okay. Now let's sort of update this idea of instantaneous travel time. It's very important to understand the instantaneous travel time, but it's easier. It's very important, but it's very easy to understand because you're just making that calculation at your trip starting time between the origin destination pair. Easy to do. Well, experience travel time, also easy, but more of a chance of making mistakes on this. Okay, because now what we say is, now you not just sort of make that decision at the beginning and read your travel time conditions on those routes at the very beginning, but now you're going to try to update your travel time potentially based on what's happening when you get to each node, each decision point. Okay. So, and again, remember, I'm showing you this very, very simple example right now, but they could be part of bigger network. These nodes could be part of bigger networks of OD pairs. Okay. So there could be another route to OD pair A, B, and C, D, and then you can basically decide how you're going to assign traffic. Now let's think about this. Instantaneous travel time. If you depart here at t equal to 1 minute, now you start to account for what time would you reach here at the second node? What time would you reach at the second node? If you started here at t equal to 1, how much time would you take to travel this link? 1 minute, right? That's right here. Now you're starting to account for that. You are going to be here. You're going to be here at this link at t equal to 2. You're going to get to this link at t equal to 2. So your travel time calculation can't anymore be based on this number. If you leave here at t equal to 2, you get to the second node at t equal to 2, and now you want to leave. Instead of taking 1 minute, now you're going to take 2 minutes on this. Make sense? Okay. So what time would you get to this node? What time do you get to this third node? 4, right? Because you took 2 minutes to travel on the second link. You get here at t equal to 4. You get it here at t equal to 4. What would be your travel time at the third link? At the third link, how much travel time would you spend? You got here at t equal to 4. Go to the third link at t equal to 4. What would be your travel time through this last link? 6 minutes, right? Because this is t equal to 1, t equal to 2, t equal to 3, t equal to 4, 6 minutes. So you're going to have to spend 6 more minutes. What time do you get here, the last one? You were here at t equal to 4. You took 6 minutes to traverse the last ring. You get here at t equal to 10, right? What is your travel time? What is your travel time through the 3 links? 9 minutes, right? You started at t equal to 1. You reached your destination at t equal to 10. So your travel time would be 9 minutes. There is another way of getting the travel time, obviously. Another way of getting the travel time would be PR time equal to 1 on this, one on this link. And PR time equal to 2 on this link. And TR time equal to 6 on this link. And you can add up the travel times. 1 plus 2 plus 6 will also give you 9. Okay? But it's a little bit tricky to be tracking this. So what I'll do is I'll pause the recording for a minute. I want you to kind of think about the t equal to 2 starting time first. Although, there are arrows here, and then we'll generalize it. So kind of, let's see if you can take maybe next 3 minutes to kind of think about what would be your travel time if you're now leaving your origin point at t equal to 2. Okay, and what would your travel time look like in that scenario to go from the whole destination? Okay, and how would you update things? So you start at t equal to 2 at the origin. Okay, so t equal to 2, how much time did you get total? Travel time? 8 minutes. The answer obviously is there, but let's try to see update it. Like, what did you put for? Okay, so yeah, so what would you do for the travel time for the first link? 1 minute, right? Still. Then you update that, and then what's the travel time here? 3, right? Because if you started at 2 plus 1 is 3, so you don't arrive here at t equal to 2. Now you arrive at 3 equal to 3, and 1, 2, 3. The travel time is now 3 minutes. Okay. And then the last one is if you arrive here at t equal to 3, you took 3 more minutes. 2, 3, 4, 5, 6, and then last one it's only 4 minutes. So if you wanted to get the travel time, it's 4 plus 3. No, sorry, yeah, 4 plus 3 plus 1. That's your 8 minutes of travel. Okay. Now, let's think about one more thing. Let's do one more thing about this. Let's do one more quick problem. What if you started at t equal to 3 now? Okay, let's start at t equal to 3. There's no solution right now. See what happens. At t equal to 3 now. Okay, so the question I've been asked is, not worry about the t equal to 3 yet. Can we talk about how does this t equal to 2, these arrows and boxes work together? So if you are here if you're here at t equal to 2, you're just basically trying to figure out the arrow represents that you started at t equal to 2 over at the origin. You took 1 minute to travel through this link, and you arrive here at t equal to 3. Okay, so now the travel time on this link will be based on the third box. So that's what it's showing you. So it's basically these arrows are pointing to what will be your travel time to these different links. Okay, so now you're going to you arrive here at, so you take 3 minutes, you arrive here at t equal to 3, you took 3 minutes. Now what time would you arrive here? So t equal to 6, right? You will arrive at t equal to 6. So now your travel time on this last link will be based on this 6th box, which represents when you what happens on this link if you start this node at t equal to 6. Okay. That answer everybody's question? Everybody's clear? Is now let's kind of extend that analysis to t equal to 3. And Dana asked us, hey, I don't see enough boxes because you might arrive here too late. You might arrive here later than t equal to 6. You might arrive here at t equal to 7, 8, whatever. And we'll figure out exactly when, but it's beyond t equal to 6. And I don't have enough boxes to figure out what is that travel time. So my answer to that is, let's assume that the travel time becomes fixed after this, and it remains at 4. It's not a standard assumption. You probably will see, you could see more boxes on top of it. But for now, let's make that assumption that this travel time remain fixed at t equal to 4. The travel time for this link at beyond t equal to 5 remains fixed at 3. The travel time for this link remains fixed at 4. And then travel time for this last link also remain fixed at 4. So let's try to quickly do t equal to 3, and then we'll try to wrap that up. Does anybody have the answer for how much would be the experience travel time if you start at t equal to 3 at the origin? 10 minutes? 10 minutes is what you got as well. So let's think about how did you get to 10 minutes, and then I'm going to stop. So start at t equal to 3. First link will take how much travel time? 2 minutes, right? Okay. So what time do you get here? T equal to 5. You started at 3. You took 2 minutes on the first link, got you to t equal to 5. And then 1, 2, 3, 4, 5. That means how much time would I take here? 4 minutes, right? Or 4 units of time, whatever that might be. You got here at t equal to 5. You took 4 minutes. You got here at t equal to 9. Okay. And then I said, t equal to 9, you don't have enough boxes here for t equal to 9. But I said, just assume that all these times are just fixed at 4 now. So you'll take last link, you'll take 4 minutes. You get here, you get at the last link at t equal to 13. Okay. So what's your travel time? You got here at 13, the travel time is actually not 13. It's 13 minus 3. And that's your 10 minutes. The other way to think about that would be individual. You write down what travel time are you taking on each of these links? 4 plus 4, 8, and 2, 10. So you can either add up the individual link travel times and get 10 minutes, or you can take the end time minus the start time and get 10 minutes that way. Okay, so that's basically, and I know you're in construction, so maybe that kind of relates to that path diagram too, right? So when they do those construction activities and do something with these, like, you know, when you end the first activity, do the second one. Yeah. Not quite the same, because I don't know what I'm talking about that, but somewhat related. Rings a bell. At least the diagrams look the same. Similar. Okay, so what we'll do is I will assign that homework in the next class, or in the lab actually today, and we'll wrap this discussion up also. Like, so we'll take maybe a few minutes of lab time to wrap this discussion up as well. Okay, and I'll assign a homework with 2 problems, one on sort of that existing traffic problem, and then one this dynamic traffic assignment. Okay, all right. Thank you. I'll see you in the lab at noon or 12:10.